Hello guys. So here's today's question. We have point-like objects that are thrown with initial speed of v0 in various directions from the top of a tower whose height is h. If the air resistance is negligible, what is the maximum distance from the foot of the tower that they can reach? Okay, what we know in this case is that the path taken by these objects will be parabolic. Uh, Earlier in an earlier video, we have shown that the focus of all these parabola or of the parabola which will be followed is at a distance of v naught square by 2g from the point of projection, irrespective of the angle of projection actually. So it actually implies what it means. First of all, therefore, that if I consider the um, projectiles or the parabolas for various angles, keeping the speed of projection the same, then the foci of all these parabola, they will be at the same distance from the point of projection. It means therefore that the locus of the focus of the various parabolas, that will be a circle whose center is at the point of projection, and the radius will be v naught square by 2g. That we have shown in this particular, rather I have shown in this particular diagram. As I said, the idea is that for all these parabolas that will be there, the for various angles of projection, but we have to keep the speed the same actually. So in that case, the distance of all those parabolas from the point of projection, let's call it as point P. In this case, it is the top of the tower as well. The coordinate system that we have chosen, the foot of the tower is right at the origin. In this case, I have shown it for one possible angle of projection. The focus is at a distance PF from the point of projection. Now we know that every point of the parabola is at the same distance from the focus as it is from the directrix. In particular, P will be also at the same distance from the directrix. That implies therefore that the circle will be touching the directrix because the radius is equal to PF and the distance is also from directrix equal to PF actually. So now let's say that point Q over here is the foot or the point where the projectile hit the floor, as the point Q, which is also lying on this parabola. So the distance of the point Q from the directrix must be same as the distance of the point Q from the focus, which means therefore that if I draw a circle through the point Q, centered the point Q, touching the directrix, that will also be passing through the point F, the focus that I have drawn in next image that you can see over here. In general, these two circles, they will intersect at 2 points. Uh, they will be the foci of two different possible parabolas, both of which have the impact point on the ground as Q. One, for example, is what we have shown over here. The next is a different possibility, a different angle of projection. For example, in this second image, we find that the same point of launch and same point of impact, yet we have in this case a different projection angle that gives rise to a different focus of the parabola, but still it lies on the intersection of two circles actually. Now different angles of projection, the foot of the impact point and P will be in general, they will be same, yet the focus will change, and we'll get different distance PQ actually. However, different angles of projection, therefore, we shall get different foot or different points of impact on the ground, and the second circle, a bigger circle that we've shown in this case, will in general be moving. There will be one position, however, of the point Q at which the second circle becomes tangent to the smaller circle, like this one which you have shown over here. In this case, the angle projection is such that the two circles touch each other, and it is quite obvious that we cannot have PQ greater than this actually. This must be therefore largest PQ, and because the height OP, which is the height of tower, is fixed, this must also imply the maximum OQ, which is the distance from the foot of the tower. So now working with this particular diagram, we notice in this case that the radius of this particular circle is simply V0 square by 2g. That length, the radius, is V0 square by 2g, which therefore is also this PF length, V0 square by 2g. The radius of the second circle, QF, is same thing as this perpendicular distance, QM, but that is equal to H, which is OP, plus V0 square by 2g. So this becomes H plus V0 square by 2g. And therefore this FQ or QF is also the same, H plus V0 square upon 2g. So we find in this case that PQ is therefore H plus twice of V0 square plus 2g, as a result of which we get in this case PQ as H plus V0 square upon g. This must be the hypotenuse of the right triangle POQ, and therefore you can find OQ, which is the greatest possible distance from which at which the ball is going to strike, and that happens to be therefore equal to root over of PQ square minus OP square. This one becomes H plus V0 square by g whole square minus H square, which I can, or you can see easily, is nothing but you can apply the factorization formula for a square minus b square to get this one to be this, and upon pulling it out, v0 by g, I can pull out what is left is v0 square plus twice gh. This must be therefore the largest possible distance at which the particle is going to strike the base of the tower, turning out to be v0 by g upon and into root over of v0 square plus 2gh. This has been obtained in this case by a purely geometrical method, and I find this much preferable over the other means. You can obviously obtain this by using a bit of calculus or using a bit of algebra. The algebraic solution I have given in the description, you can check it out. So this becomes, let me write it down, this is the max possible distance, and that will be turning out to be v0 by g into root over of v0 square plus 2gh. You may try to obtain the angle of projection at which this particular thing happens? You can comment, and well, the answer is not very difficult to find out. The angle of projection at which this would happen, which I leave it to you to find out, is obtainable as, if I just look at the angle of projection as alpha, turns out that the maximum horizontal distance OQ is obtained when the angle tan alpha is given by V naught by root over of V naught square plus 2gh, which is definitely valid if I consider, for example, height becoming 0, in which case it will be at 45 degrees, what we expect actually. So you may try to find out, and if you can verify it by other means as well. As I said, the quadratic method I have specified in the description. Check it out. Thank you for watching.